Hello, I'm a Dongjoo, PhD from UCI, and currently works at Samsung, 10 minutes from here. So today I will present our work named the DPAS. Shout out to all the guys who are helping me to publishing this paper. So please enjoy our journey of this problem. So why are we talking about I/O completion method again? Because SSDs are getting faster, and now it's in the tens of microseconds era. Once you are down at around 10 to 15 microseconds, every microsecond of the software overhead is no longer just noise. And yet, the default I/O completion mechanism is in a lot of the stacks are still interrupt-based. So interrupts are basically a fixed task: submit I/O, handler works, context switch, cache pollution, sometimes power state transition. So the device getting faster, but that task doesn't shrink. So it starts hurting the performance of the critical path. Then, naturally, people look at the polling. Here's a simple story with the polling. This is the result on our machine. On Optane device, classic polling gives us about 28% IOS bump over interrupts. Even on the TLC, it's still around 7%. And the reason the IOS gain looks bigger than the average latency drop is that interrupts don't just add a submission completion delay. They also slow down the path from the completion to the next submission, and due to implicit overhead like a cache eviction, the polling doesn't suffer from that. So the benefit compounds, but it's not free. We have to pay the cost, which is the CPU uses and others. Pure polling burns the CPU core. Under the CPU contention, it collapses. On this example, classic polling sits at the 100% CPU uses and basically stops scaling with the more thread. Latency just grows linearly, and interrupts scale much better. With 4 thread, we see around 4.5 times throughput while using around 60% of CPU uses. So the goal is getting polling-like performance when the CPU is available, but don't melt down when the CPU is oversubscribed. Hybrid polling is an obvious compromise before. Sleep first, then wake up, and poll near the expected completion. The entire problem reduced to the choosing right sleep duration. If we are undersleeping, which is wake up earlier than exact device I/O completion time, it wastes the CPU. Oversleeping, which is sleep more than completion time, directly add the latency. So, how do we estimate the sleep duration? Linux hybrid polling before did this with the epoch-based statistic. It tracks completion time in the bucket size and track every 100 milliseconds, it updating the estimate and set the sleep to half the mean. That 50% attenuation is meant to be safety margin against oversleeping. But these are shared to fundamental limitations. Epoch-based tracking has 2 fundamental issues. First, it's not a prompt. Sleep duration cannot be changed until the next epoch. Second, it's not accurate. It measures total observed I/O time, which is a mixed device time with our own oversleep and scheduler delays. So it can tell the SSD got slower from I woke up late. That turns into the next positive feedback failure mode. If you oversleep, your measured I/O time inflates. The controller interprets that as a device slowing down, so it sleeps even longer next time, and you get more oversleep. Legacy attenuation keeps it from exploding, but it takes a multiple epoch before sleep comes back down. And there's a deeper issue. Even with the perfect estimation, hybrid polling still pays a timer and sleep wake-up overhead. Context switch, cache eviction, and working set reload. So then under heavy contention, the scheduler can just wake you up late, no matter what you ask for. So the model is break. None of these 3, interrupt, polling, hybrid polling, wins everywhere. That's the I/O completion method trilemma. Interrupts are CPU efficient, but have a fixed overhead that hurts the fast SSDs. Classic polling is the fastest, but collapses under contention. Hybrid polling is compromised, but suffers from slow, inaccurate tracking and inherent sleep wake-up overhead. So our solution comes in 2 steps. PAS fix the tracking, and DPAS switch the modes safely at the runtime. So let me introduce a PAS. PAS is a new I/O latency tracking mechanism. Instead of the estimating completion time from major latency, we just ask one yes or no question after each I/O. Did I wake up early or too late? Then we can get the answer by checking the completion queue. If the I/O is still pending, we underslept. If it's already done, we overslept. That's the clean per I/O binary signal, and it doesn't get confused by how long we overslept. Then, the question is, how does PAS turn these 2 signals into a sleeping time adjustment? We turn those under and over signals, which means that the late or faster outcome into the controller. We only look at the last 2 results, so there are 4 cases. Under and under means we are still early, so we ramp sleep timer faster. Over and over, we are late, so we ramp sleep down faster. If we cross the boundary, we reset and do a small correction in the opposite direction. It's basically very tiny feedback loop with a 2-bit memory, but no epochs, no explicit latency measurement. And it converges quickly to the lower envelope. Here's what that looks like on the real trace. PAS hogs the lower envelope and reacts immediately when latency shifts a lot. Epoch-based method lag by design, then need multiple epochs to recover it. So PAS gives us promptness and accuracy with almost no added complexity. But what about heavy CPU contention scenario? Now the hard case. In a heavy CPU contention scenario, when the CPU is overloaded, the scheduler oversleep you regardless of the timer you requested. PAS sees every one of those wake-ups as over and keep cutting the sleep until it collapses to the near 0. We call this one as a time of failure. At that point, PAS degenerated into the busy polling. But with the timer overhead on every I/O. That's bad. Was pretty bad. We kind of disappointed. But it's also a really strong signal that core is overloaded. Now the question is that, can we using this failure into another signal for the other chance? So DPAS turns the timer failure into the safe dynamic switching. Think of it as a per core state machine with the 4 modes: classic polling, PAS normal, and PAS overloaded, and interrupts. In a PAS normal, we run PAS for a short proved window that give us the 2 things: whether the timer is behaving and the average I/O queue depth. If a queue depth is basically 1, meaning 1 I/O issuer on the core, we shift up to the classic polling because that's where polling bites the most. But we are only stay there for a window, then we come back to the PAS to recheck it because classic polling monopolizes the CPU and hides the contention. So if we see the time of failure during the PAS, we declare the core overloaded and move to the PAS overloaded. From there, QDEPs decide the next move. Higher QD, switch it to the interrupt. QD, if the QD is dropped to the 1 again, then recover to the polling side. The key insight is QD alone can distinguish slow SSD versus late wake-up, but time of failure can helping it, so switching is robustness and doesn't thrashing. Implementation-wise, this is a self-contained blank layer changes, small patches per core state, and no dedicated polling thread for that. This targets a synchronous port path. We're using the FIO, RocksDB through the syscall, so application can get a benefit without the huge code changes. And the hardware setup is 3 SSD classes, Optane, ZSSD, and convoluted TLC drives on the 20-core machine. We use a FIO for microbenchmark and RocksDB and others for the macrobenchmark, but I will deal the RocksDB in here. And we stress the 2 things. to break the completion method in the practice, CPU contention and dynamic I/O interference. So micro-benchmark first. Here's the x-axis means that number of the I/O thread on the machine, which is 20 core, and y-axis showing the normalized metrics. The headline for the PAS itself is a CPU efficiency. PAS reduced the CPU uses by around 21% points compared to the Linux hybrid polling, which is targeted to the 50% of the CPU uses, while keeping the similar I/O performance. And DPAS stays in a classic polling mode with a one thread per core. That's the right call. Then what about the harder scenario? Now a more realistic scenario, database workload with the both CPU contention and background I/O. Upper two graphs, x-axis means different workload, and y-axis show the normalized CPU uses and OPS. This is where epoch-based hybrid polling get confused by rapidly changing the latency, and where pure polling can get punished under CPU contention. Across our three SSDs, DPAS improve average throughput over interrupts by about 9%, 7%, 5% in different devices. And the below mode breakdown tells the story. DPAS makes the modes per core, polling when its core is free, interrupts when it's not, so it works like automatic transmission, not a fixed gear. Then, other question is, does this one can generalize it across the different SSD models? So we checked the generality, same configuration across the 12 SSDs, DPAS tops on the 11 out of the 12, and stays within the percent on the last one. So you don't need to per device tuning to get the benefit. The control signals are lowest. So the contributions are PAS, per I/O latency tracking that separate true device latency from oversleep error and react immediately, no epochs. We show the trilemma, interrupt, polling, and hybrid polling each fail somewhere. DPAS, a simple dynamic mode switcher that combines classic polling, PAS, and interrupts safely at runtime. And we validated all of this across 12 SSDs on the synchronous I/O completion path. No per device tuning was needed. The mental model of this work is an automatic transmission for I/O completion method. Classic polling is overdrive, fast, but you can start under load. Interrupts are lower gear, safe, but you pay the fixed overhead. PAS is a sensor, and DPAS shift the gears per core based on the time of failure and queue depth. Thank you so much for listening. I'm happy to take any question about this work.